Hey everyone, welcome to this explainer. I am so excited to guide you on a seriously fascinating journey today. We're going to explore the hidden universe inside our devices. We're traveling all the way from the invisible atomic-level code that actually powers a machine, right up to the macro level of how we as humans systematically fix them when they inevitably break down. So if you've ever wanted to truly understand what's happening under the hood of your digital life, you are in exactly the right place. Let's get into it.
Here is our roadmap for today. We've got a four-part progression. First, the language of computers. Second, measuring the digital world. Third, the four computing functions. And finally, 8-step troubleshooting. We're going to build this up logically, step by step.
Okay, let's dive right into Section 1, the language of computers.
To really grasp computing, we have to start at the absolute foundation to see how a machine actually thinks. Now, you've probably heard the terms analog and digital. Analog is essentially a continuous wave of information. Think of a traditional thermometer, or, the physical grooves carved into a vinyl record. The big problem with analog, though, is that it can degrade over time through physical wear and tear. But digital data? That's totally different. Instead of a continuous wave, digital represents data in discrete, exact steps using binary code, literally just ones and zeros. Going digital completely eliminates that data degradation problem. It makes information incredibly easy for machines to process perfectly every single time. It's an absolute game changer.
So how do we translate our human language into that machine language? Well, we start with decimal. Those are the base 10 numbers we use every day, like 44 or 240. But a computer reads that exact same value in 8-bit binary, which is just sequences of ones and zeros. Now, as you can imagine, those long binary strings get really messy really fast for human programmers to read. So that's where hexadecimal swoops in to save the day. It uses base 16, meaning numbers 0 through 9 and letters A through F. What this does is allow us to condense a massive 8-digit binary string into just 2 clean characters, like F0 for 240. It makes managing giant strings of binaries so much easier for us humans to handle.
Moving right along, let's jump into Section 2, measuring the digital world. We know computers use ones and zeros, but how do we measure them? It starts with the bit, which is actually just short for binary digit. It's the absolute smallest unit of data. It is literally just a single 0 or a 1, like an off or on switch. But when we group exactly 8 bits together, we get a byte. Because it has 8 bits, a single byte can represent 256 possible unique values. This makes a byte the perfect basic building block for storing a specific character. For example, in the ASCII encoding scheme, the capital letter A is stored as one single byte. Specifically, it's the binary sequence 01000001.
And once you have a byte, well, the math scales up exponentially. A kilobyte is 1,000 bytes. A megabyte is 1,000,000. A gigabyte is 1,000,000,000. It is genuinely awe-inspiring when you think about the scale here. When we jump from a single byte, just one tiny letter of text, all the way up to a petabyte, we are talking about 1 quadrillion bytes of data.
To put that massive scale into perspective for a second, think about a standard 2-terabyte hard drive you might buy at the store today. That little rectangular piece of plastic and metal holds 2 trillion individual bytes of data. That's 2 trillion individual keystrokes of text, all organized and perfectly recallable at a moment's notice. It's wild.
Now, here is something that trips a lot of people up, so it's absolutely crucial to understand. There's a big difference between how much data we have and how fast that data moves. When we talk about storage capacity, like how much a hard drive holds, we measure that in bytes with a capital B, like gigabytes or terabytes. But when we talk about data throughput, which is the rate data transfers across a network, like your home internet speed, we usually measure that in bits with a lowercase b, like megabits per second or Mbps. Remembering the difference between bytes for storage and bits for speed will save you a ton of headaches in IT, for sure.
And hey, we can't talk about speed without briefly mentioning the brain of the computer, the CPU. Processor speed, or clock speed, is measured in hertz, which just means cycles per second. So a modern 4.2 gigahertz CPU? That processor is executing a mind-boggling 4.2 billion cycles every single second. It really puts the compute in computer, right?
All right, let's zoom out from the invisible bits and bytes. Section 3, the 4 computing functions. Every single computer operates on a continuous loop of 4 basic operations. 1. Input, where the machine actually accepts the data. 2. Processing, where the CPU calculates and manipulates that data. 3. Storage, where it saves the results, either temporarily in RAM or permanently on a drive. And 4. Output, where it provides the final result back to us. These 4 functions are interacting continuously, all the time, to process data.
Let's take a closer look at step 1 with some real-world examples. Keyboards and mice are obvious input devices, but input is really just any way we provide initial data to the machine. A scanner feeding in an image, a microphone capturing audio waves and digitizing them, a webcam, a gaming joystick. These devices are literally how we speak to the machine so it can get to work and start processing. Which actually leads me to a question I want you to really think about for a second. Is your home thermostat a computer? I mean, it doesn't have a traditional keyboard. You definitely don't browse the web on it. So does it fit the definition?
Well, the answer is yes. The thermostat thought experiment brilliantly illustrates this whole concept. It takes an input, a built-in thermometer reading the room's current temperature. It then uses processing logic to compare that current temperature against your desired setting. If the room is too hot, boom, it creates an output, activating the air conditioning unit. It perfectly maps to those core functions. Understanding this helps us see how seemingly simple, everyday appliances are actually just complex computing systems working together.
Okay, shifting gears to our final macro level. Section 4, 8-step troubleshooting.
So what happens when these complex systems inevitably break down? We use troubleshooting. But listen, in professional IT, troubleshooting is not just randomly guessing until something miraculously works. As defined by the CompTIA IT Fundamentals exam, it is a highly structured, systematic approach to diagnosing and resolving issues, whether you're dealing with hardware, software, networks, or cybersecurity. It's how we ensure we fix the actual root cause and do it safely. Let's act like detectives and look at the methodology.
Here are the first 4 steps. Think of this as the diagnosis phase. Step 1, identify the problem. We gather clues from the user and check error logs. We never just make assumptions. Step 2, research knowledge bases. Has this exact thing happened before? Check vendor documentation or hit up IT forums. Step 3, establish a theory of probable cause. Form a hypothesis using logical elimination, like is it a bad cable or did they get a malware infection? And step 4, test that theory. Run quick diagnostic tests to see if your hypothesis holds up. If it doesn't, no big deal. You just go right back to step 3.
Once you finally know what's wrong, we move to the cure. Step 5, establish a plan of action. Always choose the least disruptive fix first and back up the data before making any big changes. Step 6, implement the solution. You apply the fix, or if it's over your head, you escalate it. Step 7 is absolutely crucial. Verify full functionality. Have the actual user test the system to confirm it's completely resolved. And finally, step 8, document your findings. Write down what broke and how you fixed it. That way, the next time it happens, your team already has the answer. So as we wrap up this explainer, I want to leave you with a bit of a provocative challenge. Look around you right now. Look at your phone, your smartwatch, maybe even your car or your thermostat. What basic computing action, input, processing, storage, or output is happening at this very second? Because once you start looking at the world through the lens of bits, bytes, and computing functions, everything around you starts to make a whole lot more sense. Thank you so much for joining me today, and keep exploring.